Hello everybody, I'm Brian Koziel. I'm a senior cryptographic engineer at PQSecure, and today I'll be telling you about our work on hardware deployment of hybrid PQC. So this is a happy hybrid of the NIST PQC candidate SIKE, as well as the standard elliptic curve cryptography that's seen a lot of today's infrastructure. So let's get started. So as many of you know, there's been quite a timeline of this quantum cryptography, what kind of threat we have, how soon we have to transition. And this all started when the NIST PQC competition started in about 2016. And since then, we're pretty close to getting some standardization candidates. And we're also, unfortunately, pretty close to the pessimistic view of when large-scale quantum computers will be available. So there are aggressive views, and there are also conservative views but people say that in about the next decade we really need to transition to quantum safe cryptography for our digital infrastructure. So when we do this transition, there's actually planned to be a multi-stage transition because we can't just move everything over all at once. So there are hybrid models and there are composite models. So a hybrid key exchange is one where you have two or more key exchanges incorporated into derive a shared secret. So the hybrid model is where you have a classical crypto system, for our case is ECC, and you have a post-quantum crypto system. In this case is SIKE. And you can do those in multiple different ways. You can concatenate them together in this top model. You can also just cascade them, and then the main thing though is that you have to use some hash function to kind of merge the shared secrets between them in a way that an outside adversary cannot figure it out. And so one other model that I won't be going too much into after this is a composite model, and this is where you have multiple quantum safe schemes. So let's say you have a lattice scheme, you have a code-based scheme, and you have an isogeny-based scheme. Again, you can concatenate them or you can cascade them. The main downside of the composite model is that most of the post-quantum schemes have some kind of disadvantage. So if you are already faced with a latency crisis from one scheme, you're going to be feeling the full brunt of that. If you have a communication problem for another, you're going to be feeling the full brunt of that. But for now, we focus on the hybrid scheme, which is shown above. So for our prototypes, we've noticed that a lot of IoT devices, particularly Cortex M4 devices, use a hardware crypto engine. And so one of our goals is to optimize this hybrid scheme for something that might go on a Cortex M4 device as a coprocessor. And otherwise, if you look at these devices from Nordic, ST, TI, Silicon Labs, NXP, and Microchip, you can see that each of them have an AES engine, a hash engine such as SHA-2 or SHA-3, RSA, ECC, and they can even include an RNG. So the primary reason why you want to use a hardware accelerator in addition to your Cortex M4 is just that it provides a much better trade-off between performance, security, and efficiency. So for security, you can use harder schemes that maybe the Cortex M4 can't really do in a feasible amount of time. For performance, you get a much higher throughput and thus a much smaller latency. This does cost additional area and energy, but because you're doing so fast, you can even turn off the main processor during it. You're achieving a much lower power envelope and a much lower energy envelope. So we look into the happy hybrid we call for ECDH and SIKE. So ECDH is on the left. This is the kind of like de facto standard for a lot of things. It has a very small public key sizes and it's fairly efficient to compute. And SIKE on the right is much more complicated, albeit it's still related to mathematics on elliptic curves. And this is believed to be secure in the face of large-scale quantum computers, which is very nice. So SIKE actually has the smallest public keys of any post-quantum scheme. It's about an order of magnitude better, but it's about an order of magnitude slower. But for our purposes, we want to tie these two together because the computations are really similar. So what we do is we propose SIKE curves that are very efficient for ECC. So if you look at the SIKE documentation, there are 4 parameter sets for a 434-bit prime, a 503-bit prime, a 610-bit prime, and a 751-bit prime. These are necessary for SIKE to be secure. These prime sizes are a bit larger than what's needed for ECDH, but that's fine because it'll still correlate to a strong enough security for classical ECC. The main problem, though, is that the SIKE curves are good for SIKE, they're good for computing isogenies, but they're actually extremely vulnerable to the elliptic curve discrete logarithm problem. So what we do is we propose new and better curves that use the SIKE primes, but are no longer weak to these polared row or other attacks on elliptic curve Diffie-Hellman. And so we use primes. We propose curves at each of the 4 primes: 434, 503, 610, 751, and we find these primes using a similar method as the X25519, X448 curves, as proposed in RFC 7748. So just basically, like, if you look at what these curves are, they're secured by the safe curves criteria, so their the order of the curve is extremely large, the order of the curve's twist is extremely large, a polared row attack is no longer very efficient on this, and there are a lot of other nice metrics that you can look at the safe curves criteria for. In addition, we also look at and propose some curves for EDDSA, elliptic curve, Edwards curve digital signature algorithm, and we use the RFC 8032 standard as kind of a method to find those curves. And overall, for our X curves for ECDH, we have that the public keys are about 55 to 94 bytes larger. So for a smaller device, you're expecting about a 55 byte increase from the SIKE parameter scheme. So this table summarizes the curves for ECDH, or the X curves. And so, as an example, if you look at SIKE P434, this is NIST security level 1, which means that it is as secure as AES 128. And it has a public key of 330 bytes and a ciphertext size of 346 bytes. For a corresponding ECDH scheme, we found an A coefficient in the Montgomery form shown below of 439,322. If you have a base X coordinate of 4, then this provides a very secure ECDH scheme. For instance, one safe curves criteria, the polared row attack is 2 to 250 power, very secure in the face of classical computers. For ECDH, this corresponds to also about a 55 byte public key size, and so if you add the public key to the SIKE public key and the public key to the SIKE ciphertext, you get 385 bytes and 401 bytes for our proposed SIKE-X scheme, which is a hybrid of SIKE and the X for ECDH scheme. So put in another way, this graphic shows a simple key exchange scenario. So we're using ECDH and SIKE to achieve a shared key, and we can use AES based on that. So starting from step 1 and 2, we just use ECDH and SIKE's scheme to generate a public key. And so we use E to derive to show that it's ECDH, and S to show that it's SIKE. So the ECDH key is 55 bytes, and the SIKE key is 330 bytes. And on the other side, after we send this, the other party is going to compute the ECDH public key and shared secret for their own private key. So for convention, SIKE uses a ciphertext on the way back, so we consider that's what we call it for ECDH, the public key. So they generate the ciphertext for ECDH and the shared secret for ECDH. And there is one single operation for SIKE called encapsulate that generates both the ciphertext and the shared secret. So based on these two shared secrets, we can derive a shared key for AES, and we do that using a key derivation function. So this could be a hash, it could be a variety of different things to increase bias. And so we send these back to the first party, and again, they're going to finish the protocol by finishing off both schemes. So ECDH is a compute shared secret, and SIKE is a decapsulate. and both of these produce shared secret. We call them prime, and if you do a KDF for this, it should be approximately equal on both sides. This Z on the client and this Z on the server. So then you can use some kind of shared AES scheme, such as AES-256 CCM, to exchange encrypted application data between each other. So this is the SIKE X434 scheme, and as a proof of concept, we wanted to see how big this would be in, like say, as a hardware coprocessor. So we tried to design a SIKE X434 unit as small as we could, and these results are actually smaller than this smallest SIKE 434 unit that we've seen in the literature. So like we chose some design decisions such as using only a single port block RAM, so it's about 4 kilobytes. And inside the SIKE X434 unit, we have an elliptic curve controller. So this is going to control all elliptic curve operations for SIKE P434, which includes some isogeny stuff, and the Montgomery ladder used by X434. We have a Ketchak unit. So a Ketchak is the sponge function of SHA-3, and this is used for SHA-256 in the SIKE scheme. Ketchak is a very small proportion of the entire latency, so we made this kind of as small as we could. And then lastly, we have the modular arithmetic unit, which is the bulk of this design. It's 35 kilogate equivalents of the 46 kilogate equivalents. And so this computes modular multiplication, modular addition, modular inversion efficiently for the SIKE P434 prime. And one main advantage of using one single prime is that we can optimize this modular multiplication, for instance, using Montgomery multiplication very efficiently for both schemes. So then when we look at performance, we just wanted to compare against a simple M4 implementation, M4 being the most optimized, assembly optimized scheme there is right now, to our hardware optimized. So as you can see, we have about 3 to 4 times improvement in cycles between the M4 and the hardware implementation for just SIKE, and this is purely in terms of latency. So our hardware can run significantly faster than the M4 can, depending on what kind of application you are running. But then when you look at the SIKE X434 results compared to the regular results, you can see that we have only a few, like less than 10% increase in latency for these operations, which is great. It shows that the computation latency isn't that high. Overhead isn't as high for when we include X434. When we look at a breakdown of all the timing, we see that X434 operations for key gen and key agreement, so these would be performed twice, one from each party, is about 2% of the SIKE operations. If you look at SIKE X434 operation, you see that it's actually dominated by the encapsulation and decapsulation time. So the expected time is mostly going to be either one encap or one decap for a party, because key generation is only going to be done once, and you only have to encapsulate a key or you only have to decapsulate a key to get a shared secret. So to summarize, this is the happy hybrid SIKE and ECC. For SIKE, it has the smallest public key sizes, which you can match well with ECC to only slightly increase the total public key size. It is similar computations to ECC, and it's also a very simple security that has been continued to be improved. Like we've had smaller parameters throughout this PQC competition. So for here, we showed a small implementation of SIKE X434, which is a hybrid implementation of X434 and SIKE P434. We are working on faster implementations. Actually, the bottom point, we have an implementation that triples the performance for only a small area increase. So one comment is like, why don't you use already standardized curves like X25519 or X448? If you look at how SIKE works, we have to use the SIKE smooth isogeny-friendly primes. And if you don't, it's going to be a performance hit that won't make SIKE feasible in any way. and so we can't really take advantages of the X25519 or X448 primes, and so we can't take advantage of their fast, say, modular reduction or something like that. So, but if we wanted to still include them, we could do that, but that'd be more ALU area to support that, more control logic, and it would be only a small increase in, say, performance overall. So ED25519, ED448 are a similar story. We'd like to also get some more hardware results of those soon. So new curves based on these primes save area and hardware for these accelerators, which is our focus. And we want to see if these are the final curves. If P434 is the final curve for SIKE, then I think it would be a great idea to work on, say, standardizing these so that hardware can take advantage of it. And this will help reduce the power, energy, and timing envelope of smaller devices that use a hardware coprocessor. So, kind of like in conclusion, SIKE X434 only requires a small increase in communication bandwidth overhead. So for P434 is still less than 400 bytes, which is still smaller than any of the other PQC public key sizes, and it only has a small increase in the total performance. So again, this is our happy hybrid SIKE X434, and please feel free